have a finite set of data. I don't know what the true distribution of the data is, so you do this empirically, right? So empirically is what you do this. So I get some data, and now I just take an empirical estimate of this expectation. And now what the no free lunch actually says is I can come up with a combination of these things that makes this take an arbitrary value. That's basically what it is, right? So now how do we then proceed in this scenario? How do we actually manage to learn? Because this basically says you can't learn anything from data. So you have to put in additional information, exactly as you guys put in additional information and laughed at one explanation and not at the other. So let's say that we put prior information about our learning algorithm, how we search. To me, that's a little bit like this. So I decide to, right, I got this space that I'm going to search in. I don't want to go there because I don't like them. Okay, I cover my eye. And then it's like, I don't want to go in between there. So I'm going to put really big shoes on so that I can't get through that door. And then I'm going to do like the Academy of Silly Walks to end up in the solution that I want. This is a lot what's happening in the neural network community. If you think about early stopping, dropout, and all these things, they have very little intuition, but basically that's what they do, right? Now, another thing you can do is you can say, well, cool, I'm going to take a biased sample. I'm going to make sure that I pick the data so that I learn what I want. This is like if you've heard of things like data augmentation. So I say, oh, I don't want it to learn that the rotation is important. Well, actually, let's rotate every image that I have, and I hope that now that removes that valid explanation. This is really hard because it basically implies that you know what you want already, right? And it's also incredibly costly. So the other thing, and which is just what we've talked about now for 2 days, is saying, can I put prior knowledge about the hypothesis space? And that's GPs, right? It's saying, you know what? Given these types of solutions that I'm interested in, these hypotheses in terms of a regression problem, if the very smooth function and the very, very high frequency one fits equally well, I prefer the smooth one, right? So that's basically what GPs are. So I wanted to just put that in a little bit of context in terms of learning theory. Cool. So then there's another part of machine learning which we often forget, right? And I like to draw this graph. So there's 2 ways of solving a problem from data. One end is, I used to say, data and assumptions. So if I've seen everything that's ever going to happen, ever, the only thing I need to do is enumerate the data that I have, and any question can be answered by a lookup table, right? The other thing is, I've never seen anything before, ever. Now I need to add a lot of assumptions and beliefs about this in order to reason at all. So now machine learning lives somewhere on this scale, right? Now, personally, I think the narrative has been that, cool, we're learning so much about clever machine learning techniques so we can move up here and do more and more assumptions. But really what's actually happening factually is we're moving down this spiral or this slope and saying, you know what? I can just use data rather than making assumptions, right? So now, what does this actually mean as well? So we say that GPs are very data efficient. So what that means, and I hate this word, the word flexible, but I'm going to use it. In our group, it's known as the F word. But basically, when we say that these models are very adaptable, GPs are very adaptable, but they have the really, really cool characteristics that the distribution that you put over the space of functions is actually very, very concentrated. And that's why they can use a little, small amounts of data. Your assumptions are actually really, really strong in what to do. And that's cool. So it's very important to remember this, that as soon as you see something learn efficiently with small amounts of data, that implies that it makes a strong assumption. And what I wanted to get to with this was that over the last couple of days, and it's a natural question, I've asked it myself, you see all these cool stuff. Nicolas gave a really good talk about kernels, and the question comes up, how can I automatically do this? I'm sorry, but this is the wrong question. Because the question should instead be, you can't do this. Fundamentally, it's impossible to do this, and you shouldn't. What you want to do is to say, oh, I've been taught a really cool tool and a handle to put in my prior knowledge. That's what you want. And anyone, and we still read papers that says this, cool, I got this paper, I'm doing this, I've reduced the data load by a half, and I make less assumptions. Well, that's bad. The paper I want to see, I made so many assumptions, so I didn't even need data. That's knowledge, right? Right? And it's on that spectrum that we have to work. So just remember that. Cool. So then I just wanted to mention, just to highlight this again with GPs. At one point in time, there was this Latin thing under this school, which is that the posterior is the student of the prior. And I just think this is a very, very nice saying, because basically everything that we talked about today or this week has been the prior. And the prior is the important stuff. The posterior is just math to get there, right? Most of the things we've talked about, or a lot of it, has been how the hell do we need to get to this point. But the cool thing that you should think about is think about GPs. Are they a good handle for me to insert prior knowledge? Good. So then I'm going to continue on with the actual talk. So what I'm going to do is that I'm going to talk about unsupervised learning. I'm going to talk about models. So far we've seen a lot of techniques. I'm going to show these are kind of cool things you can do to design models for different types of data. And then I'm going to talk a little bit about deep GPs in the end, or quite a bit actually, about composite modeling in general and the challenges that it has. But just to, before I do this, that, you know, when you become a lecturer, you keep saying, I did this, and that's no longer true because I didn't do pretty much any of this work. So I'm very fortunate. So me and Neil Campbell, who's going to be here in a couple of days, runs a group down in the southwest, and we got a lot of really good people working with here. Aidan is over there, and Yeva, who's going to give a talk later in the afternoon, is probably going to tell you how it's actually done. But for now, I'm going to show their results at least. Cool. So I'm going to first now give my toy view of how Gaussian processes work very, very quickly, because this is the way I see them, and because this is really the thing that we should all leave and be very, very clear about, right? So I said that I want to specify priors and beliefs over the space of functions. Great, that is a space, and apparently there's functions that go across it. That's what I want to do. Well, that's weird, because naturally we all think about parameterizations of functions, but then I'm already limiting myself. So what we do when we think about GPs is that we think, what is the one thing that's always true for every function? Well, if I look at a line at this 3 here, what I know is true for every function is that this line has to be crossed once and only once. So instead of placing a distribution over the space of functions, I specify a distribution over the instantiation of the function at this point. And we say that that's Gaussian. Now, there's nothing special about 3. If that's true at 3, it's true at -2, right? And if it's true at those points, it's actually true everywhere. And then that's a GP, or a GP prior. So what I actually did now was Kolmogorov's extension theorem backwards. What says that the two things that needs to hold for a stochastic process is that every marginal has to be the same, and that it's invariant to permutations of these marginals. And that's exactly the two things I did. I said 3 and -2, same thing. And actually, if I look at all these marginals, it doesn't matter. So I just did what's, yeah?
Can you repeat, like, when you put the 3 line, what are you, yeah, what
So,
do you mean by this? Yeah, so.
basic, good. Super good question. So what I say is that I need to think about functions. Can't think about functions, but what can I possibly think about? What do I know that's true for every function, right? So just limit this space somehow. Well, if I look at this line that goes here, I do know that any function in this space has to cross that line once and only once. So what I can do is that I can say, can I have a belief over where I think the function cuts this line? Well, I'm going to say that that belief is Gaussian, I have a Gaussian distribution of where I think it cuts it. That's just the one-dimensional Gaussian. Now I said, well, actually, that's true there as well. If I made that argument, it's probably true everywhere. And now it's infinite because this index set, this is the index set of the GP, is infinite, right? So now I got a stochastic process. And the only thing, yeah?
So interestingly, that already puts an assumption on something because it doesn't allow discontinuities.
Yeah.
But you could have been unlucky that exactly that point there was a discontinuity and therefore you wouldn't have a distribution.
Yeah, so this is absolutely true, right? Now, the tricky thing with this is that you can't give me samples of a discontinuous function to show that it is discontinuous. Because any samples that you'll get, how many points are there between, you know, infinitely many, right? So any function that you give me samples of are going to have a non-zero probability under this thing. But the truly discontinuous function, I can't have samples that proves that this is discontinuous, if this makes sense, right? So I wouldn't draw a sample that's discontinuous, in a way. But if that makes sense, right? Cool. So the only thing that we then design with GPs is that we say this. Cool. What if I knew that the function at -2 was this? Well, let's say that I knew it and I had a little bit of noise around it. What we parameterize with the covariance is that we say, what information does knowing -2 tell me about 3? That's the only thing that we parameterize with the kernel, right? So one way is to say, well, it tells me nothing about it, so it's back to the prior, or it tells me everything about it, or probably it's somewhere in between. Now that is your fall-off in covariance if you write a smooth function. So you say, well, actually, the variance of this one depends on the distance between these two. And that's how you design it, and now you can also get a feeling for, well, you can design this however way you want, right? How do you do a periodic one? Well, you say that, cool, this one, very high, then it comes back to it's a copy of it, so forth, so forth. And designing that type of function is how we specify priors, right? Hopefully this is clear, but this was my engineering-y way of explaining it rather than the beautiful math that you've seen so far. Cool. So that just leads to the conditionals, blah, 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 and that works very nicely. So if there's one thing that I would recommend everyone to do if you want to learn Gaussian processes properly is to derive all the Gaussian identities by hand. It's something that I had to do it when I taught the machine learning course because people just kept asking me, and I'm like, I don't actually know this, I've just taken it for granted. Actually do the derivation of showing the marginal and doing the conditional. It's really worthwhile. And if I have in my machine learning course a PDF going through it quite detailedly, that's a link to. But I really recommend you to do that because then you see how really simple these things are. And it's a very useful thing to have done once. Cool. So now then, let's come to unsupervised learning with GPs. So far, we've done supervised learning. So we've done this kind of thing where we've been interested in learning marginal distributions. The distribution where I say, given this x, what do I believe the intersection at that line is? That's the thing that we've done. So we've had an x that's been observed, and we have a y that's observed, and then we put this function prior on it. Now what we want to do something that people call unsupervised learning, where we say, actually, what I'm interested in, I only have y's. So I want to learn the distribution over y. So now this thing here is also unknown. So let's make a schematic of what that actually is. So the way I like to think about it is this. So let's think about it a regression problem, but I don't know the x's, I only know the y's. To me, this is like having an abacus frame. So I have all these balls sitting on one end, and I got these rods, and my task is now, can I move these and give each one of them an x value, right? That's basically how it would work. So I can do that. I can move them like this. Cool. That's something. I can move them like this. That's another one. I can move them like this, right? So now our space of hypothesis needs to be, which one of these do I like? Right? All of these function perfectly explains this data. Now we need to put this selection process into this. So therefore, we place a GP prior over how this relationship should be, right? So you can think about it. I've just fitted some GPs here. This is fitting a GP to the points looking like that. It's fitting a GP to points looking like that. And that's another one like this. Cool. So hopefully you can see that if you would take all of these structures, have a fixed GP prior, and evaluate them, which structure is most likely under the prior, you will get a score, and then you effectively pick the X structure that's most likely, right? That's one way of doing it. But there's a slight problem here. Namely, this happens very often in modeling, there's a get-out-of-free-jail card for the model. So say that your GP prior really likes lines like this. Well, what I could do is if I push this one to minus infinity, this one to plus infinity, and you stretch it massively, the line just gets flatter and flatter. And I can push them really close together, and the line just goes like this. And if my GP prior is that I want things that doesn't have a very big slope, well, cool. I'll just move them super far away then, right? I can make a line out of anything that way. So this is something that we often have when you've got multiple objectives and they're kind of competing. So my example is that I really like to eat good food, but I also want to eat it reasonably quickly. So I don't want to cook for 11 hours. And if my objective is that it wouldn't turn out quite nice if I did that, but you know, if I just have the objective of eating well, I'm just going to stand there cooking and never eat, right? Something like that. So what you need to do with all these models is that you need to balance it. You need to have priors for both the function and for the locations of these points, right? Otherwise, it's not going to work. So what we would then have to do is that this would be our model. I have a likelihood function that says, if I know the function, this is what I think is a likely generation of data under it. The GP prior that says, at these locations, I think the function values is this. And I have a distribution over X, for example, could be a Gaussian blob that you say, you know, don't go out too far away, keep it reasonably small. So now, F then specifies my belief of what I assume or what my definition of is of a complex function. And this one says, what do I assume or what do I believe a notion of complexity is for the input space. So now, cool, let's just turn the handle and we're done, right? So now, there's a tricky thing here. It would be way too easy if this was the case. So let's now just look at the GP prior. So the GP prior looks like this. So it's some Gaussian, which is some exponential. Inside the exponential, there's an inverse of k. K itself, each element is an exponential with an x in it. So the x comes to f through this exponential inside an inverse inside an exponential. And then this is supposed to go through the likelihood where f now is all these weird relationship inside an exponential itself. And then if I make x also a Gaussian, then I go another exponential. You do not, yeah? Shoot.
Quick question about the prior. So I'm trying to think if you have like your data.
Yep.
Like so this prior would be like an assumption on the training data that you have. Like you have some data and then you did use it, for example, the smoothness or whatever.
For example, yeah. For example, yeah, it's how I think that this function looks like. But now my degrees of freedom is that I'm allowed to change the input location. So if you think about it, if you had that abacus that was infinitely long, you can create any location of those function points, right? You can just move them anywhere. Now you've encoded a belief that says, I prefer this one more than that. This is flat Earth, this is not, right? That's what your GP prior does. So for example, flat Earth might be a very wavy function. The other explanation is a very smooth function. So now if your prior is very smooth, you're automatically going to choose the one which makes a nice curve, right? or the other way around. So it's just how you encode your belief, or as I like to say, your notion of complexity. You say, this is a very complicated explanation. Like flat Earth is a really, really complicated explanation of how the world works, right? But that's not true for a lot of other people who think it's the most natural explanation of why the world works the way it does, right? So you can kind of see that trying to integrate out x from this thing is going to be a horrible business, right? You see the relationship between y and x is like super nonlinear and super complicated. So what it actually is, it's like this is completely analytically intractable. So it's a non-elementary integral if you would try to do that. So that means it has infinitely many terms. It's also infinitely differentiable the way I've picked it now. So you can't do a Taylor expansion in any form of sensible way for this either. So this is just really, really hard. So this is a funny one. So Neil normally talks about Laplace for an hour and a half in his talks. Now no one's mentioned Simon Laplace, but he's like this house god for everyone. So Simon Laplace apparently said this: nature laughs at the difficulties of integration. So this is what I meant with often the priors. That should be easy and sensible to understand. Getting the posterior is damn hard, right? And this is basically one of his nice quotes. So what we need to do is to do approximate inference here. And you've seen a lot of the approximate inference so far. Alan talked about it in terms of likelihoods. And Jen talked about it in terms of sparsification. And I'm going to use quite a bit of these methods, but I'm going to go one step further with this. So the first thing that you would do, this is not approximate inference. Well, it's wrong, but the first thing you could do if you throw principles out the window is you can do a maximum likelihood estimate. You can just say, well, actually, I'm not going to specify distribution over x. I'm just going to optimize the damn thing, right? And I'm going to put p of x as just a regularizer. So if you would do that and just do a maximum likelihood estimate of this, you would just take this thing and minimize this thing based on x. And this you can do. And it actually turns out it worked brilliantly, beautifully well. So there's lots of papers on doing this. People spent a long time doing this. I spent a long time doing my PhD exploiting the fact that Neil cracked this or decided to optimize the x's at one point. So it worked really well. There's a really cool demo, if you want to get a feeling for this, which is by Neil Campbell, where he has a two-dimensional input space, x, but an output space which is 2048 dimensional, which is the outline of a font. And in this demo, you can move around in this space and you can generate different characters. And it's really beautiful. So that's a clickable URL, so you can try that. So, except for just being wrong, there's lots of challenges with doing maximum likelihood estimation. How should I initialize x? I don't know. Like, I need to pick an x, right, if I don't integrate it out. So how should I do that? What's the dimensionality of x? Should it be 2, 4, 8, 19, 297? I don't know. So I need to pick that. This is really hard. And I have no means of actually learning this because I haven't said what I prefer, right? This is a setting where I haven't told you which x's I believe in. So it's just I have no notion of being able to learn these things because this implies encoding a preference towards something. And what this actually means is that my assumptions of the latent space does not reach the data because I don't integrate it out. I just use it as some stupid regularizer on the end. So what I need to do is approximate integration of this. And you've seen a lot of this. So I'm not going to go through variational base yet again, but I'm just going to go do like I did with GP. So I'm going to give my quick twist on this. So what we have is that we've defined a model, x to y, right? This is what I've defined, right? I have some latent space, I don't know what it is, and I have some data, and I have some GPs and stuff in between, but let's just simplify it. It's something that generates something else. Now, what I want is this object here. I want to have integrated out this thing. I've now shown that this is impossible. I can't do this. So I can't solve this integral. But there's another way of writing this value that's not an integration. I can do base rule. I can write base rule in a little bit of a confusing way, where I say p of y is equal to this, where this is what I've specified, this is what I've specified, and this is the annoying posterior. But now there's no integral, at least. So one way to think about this is that if I want this object, I can also search for this object instead. Because if I know this object and I know this one, I can get this one. So these are the two problematic terms, and I can choose to pick one of them. So what we're going to choose is that we're going to choose, and this is what variational inference does, we're going to choose an object Q that's going to try to fit to this thing. And if I can fit to this thing, I will have this thing, right? So we avoid computing the integral by approximating the posterior. And I think this is important because I don't like thinking about variational base as learning a posterior. Because why the hell would you want to learn a posterior? You want to learn the evidence of the data under the model, and the posterior you get if you've done that, right? So the way you do this, right, and you've seen this derivation the other way around with the KL divergence, is you're saying, I want this object. I'm going to take the log of that object, just because I like to. It makes things simpler. Then I can, now, I said, this posterior would be nice to have, right? Because I'm going to focus on this posterior. Should be a dx there. So I'm going to add this term. It does nothing, right? It's just log of 1, so it's gone. And then I'm going to merge these and say, cool. So now, because I want to merge them, I kind of want to have an integral over this one as well. So I'm going to add the distribution Q, and now I have to integrate it out from this one, and I'm going to have to integrate it out from this one. Then I'm going to join these integrals and just write it like this. So now, then I'm going to take this thing here and write as the joint distribution. There. I'm going to take out the posterior and put it in this term here. And then I'm going to add this term that does nothing, because it's still just log of 1, or log. So now, what I can do is I can move these objects a little bit around, and I can get to q log qx, and I take this qx here, and I move it over there. Now you have exactly the terms that Alan described before. I got the entropy, I got the expectation Q over the joint distribution, and I got the KL divergence. The reason why I don't like motivating this from the KL divergence, just moving this over there and deriving it from the KL, is this is the only object we don't compute. So why would you motivate variational base through the one object you never use? This just seems weird to me, right? Have I dropped the minus? Q, 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 2, 2, 2. So that Q there, so this one goes there. I don't think I've flipped anything yet. I'm going to flip it soon. I'm going to flip it the log soon, and then they're going to be mine. Very likely I might have.
There is, because you've like moved your bottom Q of x to the right.
Oh, this one needs to be minus, right? This one needs to be, sorry. Yeah, perfect. This one needs to be minus, yes. Very good, very good. Don't write slides after going to the pub. But, so I like to see it this way instead. So now we can just look at this object, right? Just to show very simply, right? So I look at this object here, and that's my KL divergence. Now, what I'm going to do is that I'm going to flip this around. Inside the log, I get the minus. And then I can now do the Jensen inequality by moving this thing out here, right? And now I got this thing here, which I know is a distribution that integrates to 1, so it's 0, right? So the only thing I've shown here is that the KL divergence is always positive, right? That's the only thing I've shown. But the important thing with this, so now you question, well, so this is the formula that I basically wrote up, right? If we go back, and I said that this is always positive, so this thing here is a lower bound on that. So now there's one question that you can think about. Why did I use the log? The only reason I got a KL divergence was because I had a log there. Well, you can use any monotonic function as long as you can do the Jensen inequality to bound this. And that's a whole class of divergences called F divergences, and different ones have different properties. So to me, the only thing you need to do is you write up the evidence and then you find something to bound it with, whatever now that is, and different things have different properties, right? But to me, you don't minimize a KL divergence. That's a strange thing to me to understand, at least. Cool. So if we could do this, then we get these two objects. Because I get this object here, Q of x, it's an approximation to my posterior. Great. That's what I want to use as prediction. I'm also maximizing P of y, which is effectively learning. Nice. That's the setting that we want to be in. So why is this a sensible thing to do? Well, in Talking Machines, before Neil hosted it, Ryan Adams said this really nicely. He said, if I can't formulate the joint distribution, there isn't much I can do. We're taking in expectations over the joint distribution. If you can't formulate your model, you don't have an inference problem to begin with. The next thing is, I take a log of the only tricky distribution I have, which is the joint. Well, the log is usually easier to work with than the actual distribution. This is probably the motivation why you think KL divergences, but you want to use something that makes the distribution easier to work with. And secondly, or third, you're allowed to choose the distribution Q that you take the distribution over, right? So given all these freedoms, you should be able to compute this. So let's just do this with GPs in GP-LVMs. So the different setting now is that we need to integrate out x, right? No one's done this so far. So we just say, cool, I'm going to have a Q of x and a Q of f as well, I should have had. And now I want to integrate out x from this, but let's just focus on x. So what can we do? I can now write up my joint distribution as my model here. So likelihood prior and prior over x. And then I churn the handle a little bit. I take the QP out. So I got this term here, which Alan said this is just a regularizer to make sure the Q stays close to the prior. And I got this object here. So that's what we want to work with. So I'm going to call that L tilde. So now it's this object. So if we look at this, have we done anything to help anything, really? Not really, because my problem was that x went through f non-linearly to go to y. And I haven't solved that at all, because if I want to integrate this, I have to take x non-linearly to f to y. I still can't solve this. It doesn't help me at all. So variational base just doesn't work on GPs in the general setting if we want to integrate out x. It doesn't actually help us. So what we're then going to do is we're going to use what Genwen talked about, which is a sparse approximation, but we're going to use it slightly differently, and we're going to interpret it slightly differently. So what we're going to say is that from this GP, I have an additional set of points. Remember, it's an infinite index set. I've indexed it by my training data. And then I'm going to set, I also have an additional set of indices. I'm just going to add a couple of more things that I can evaluate on. And I'm going to call the output of those U and the input of those Z. So U lives in the same space as F, and Z lives in the same space as X. I'm sorry for the notation, but it's not my fault. These papers that describe this was brilliant work by Michalis and Neil, use very confusing notations. And the two papers, and they also changed the notation between them. But think of this as F, and think of this as X. So now, one thing that we know with GPs, which is very, very nice, is that if I then write down the joint distribution of this GP prior, so FU XZ, I can now write the conditional distribution. I can just factorize this with the product rule and say, now I got UZ, and then given that I know U, this is what the F would be, right? I've just done the product rule. So now that's here, now just become the predictive posterior. You've seen this as. This is saying, like, can I predict F if I know U? So it's going to be this formula here, So this here is the predictive posterior that you've seen before, and then this is just the GP prior. Right? But remember, I don't know U, or F, or Z. So now what we're going to say is that we're going to again formulate the lower bound, but we're going to use this extended model where I now have U here, but importantly, I'm not going to put Z on this side. You can, but I'm going to keep Z here on this side. So now what I would have is I got my prior over X, I got my likelihood, I got my predictive posterior that takes U and predicts F, and I got my GP prior over U. Okay, so you've done nothing with this model at all. You just said, initially I wanted to evaluate this index set, now I'm just going to extend the index set with a couple of points. Okay, so now we will change the should be Z. Now we're going to change the interpretation of this slightly. So rather than thinking of this too as just parameters like indices in this GP, we're going to think of them as the parameters of the distribution Q. Yeah? So we're going, yeah?
So we are assuming independence of X from U, right?
X from U.
Because if not, it seems like in the last
Yeah. This is the definition of a stochastical process. You have to do this. So in the definition of a GP or any stochastical process, if I condition on this subset of the data, this doesn't change if I now condition on this plus this. This marginal is always the same. That's the definition of a GP. You can think about that. The way I drew them like this, if I look at this slice, if I now say, cool, I'm going to look at this slice plus this slice can't change. Yeah. That's the definition of a stochastic process. Yeah, we can talk about that later. It's a good comment though, but effectively they are. So now we're then going to say that I'm going to approximate or parameterize my posterior using these parameters, or my approximate posterior. Well, so now remember then, so what I want to integrate out, what I want to have these Q distributions over is U, F, and X. So remember these things are now supposed to approximate posteriors, right? So this thing here is supposed to approximate this. This thing is supposed to approximate this, and this thing is supposed to approximate this, okay? So what we're going to do, and this is a very, very important point why this works, is that we're going to say that the problem that I have to represent F, U completely represents this function. So what I'm basically going to say is that U is sufficient statistics for F. So what that means is this thing here, QF, was supposed to approximate this posterior. And now Y, remember Y was the observations, the noisy observations of F at X. Now, if this is true, if U is sufficient statistics for F, I don't need Y here. This thing here, I can drop Y. So what this basically means is that U is supposed to completely capture all the statistics of the functions. Another way of thinking about this is that I got infinitely many basis functions, like this in the GP. Now I'm going to say, you know what? You don't need infinitely many basis functions. You only need a couple. I don't know where they are, but I'm going to find them so that these are actually sufficient statistics for describing the function. That's basically what it says. Yeah?
Why do we still need X then?
You still need, very good. The reason why we need X is because it's a stochastic process. This is the index set. If I don't know where I ask the question, I have no idea what the function is. Because our distribution, as we said in the beginning, a GP is specified of what is the function value at this point. And if I don't know what point I'm asking the question of, now I have no idea, right? So I still need X to know where F is.
But we have Z, right, which is also an index.
Yeah, Z defines where U is. Yeah. And because this is from the same GP, the way you can think about this, to say how the U's work together, I need to compute the correlation, and the correlation is computed based on the inputs, right, which is Z. So think about the GP, this GP here. This is just your normal GP, right? You couldn't say anything about U if you didn't have Z, right? Right? So now that's just your normal GP. This one here is you saying, I need to be a Z there as well. So here, this is saying, well, I know I've evaluated the function at Z, and I got U. Now I want to ask the question, what are the function values at points X? Well, they are F, right? So that's what it says. So think of these as the F points. So the index for those are X here. Now I'm going to say there's another set of points. It might lie somewhere like this. The index of those are U there. Are Z. The outputs of them are U. Now I want to know what the function value is at these points. And what I'm saying is the only thing I need is that I need to know this and where it was. And I need to know where I'm going to ask the question. Right? This is the non-parametricness, right? I need to know where I want to evaluate the function. Right? Okay? So this is what I'm going to assume. And now something very pretty is going to happen. So now we write this big thing up again. Wanted to integrate f, u, and x. Boom, I have this, q of f, q of u. You remember in the first slide I took out q of x, right? So otherwise it would have been a q of x, but this was my L tilde, right? So I have to add that thing later on. So now we're going to write up this as this. So likelihood, predictive posterior, prior, q's. Now we're going to introduce this distribution here, which is basically saying that I said that this thing here should really approximate the thing with y, but now I can drop y. Now we're going to introduce that. So now if I introduce that, you're going to see this thing here was what I had outside. This is my q. Then I have the log, and now I have likelihood, predictive posterior, this. Now the posterior that contains y is now going to be the same as the posterior up there. So now this term and this term cancels, right? Because of the assumption that I don't need y. So now if I cancel them, what have I done? I've done something really, really cute, because now if you look at this thing here, I've disconnected x from y. Because I've said that all the statistics of this model should be captured by u and z. And u and z are parameters that I'm going to optimize. So now this thing here is not a problem. None of these contains nasty integrals. Still have to integrate over these distributions, but that's fine. So if I do that, I end up with this thing, and I'm going to have to add the KL divergence from the previous thing. So I have the KL divergence to QU, which is the output of the inducing point, we call them, to the prior of the inducing point, same behavior as before, and I got this expectation here, which is just over the likelihood. And this we can do. So now this here, this integration here, is tractable for some covariance functions. Neil talked a little bit about these, calling this size statistics. If you can't integrate it analytically, you can always sample. Because you're sampling in a bound, you're still having a lower bound, you're now drawing samples, it usually works quite well. Now, the nice thing, which is what we're going to talk about in terms of unsupervised learning, is that look where x appears. X only appears here and this. So if I want to specify some batshit crazy idea of what x should be, Well, it's super easy. It just ends up on top here, right? It's kind of outside the computation, which is really, really nice. So that's what we're going to talk about now. So I'm so running over time, but this was basically the theory part that I was going to go through, and now I'm going to talk about stuff that we can do with this. So basically, the thing that I've done is just saying, we've seen the variational bound several times. We've seen the sparse approximations a little bit. We saw them for computational benefits. Now, there's an additional thing to integrate out, x. It's harder because effectively it's further up in the graphical model. It needs to be pushed further to get to the data. Now we said, cool, let's use this as a means of actually integrating out this thing. So now we have a bound on this model. That's it, right? And I know getting through that math is a little bit daunting, but it's actually not. Think about it as the basis function thing. You don't need infinitely many basis functions, but if you say, I don't know which ones to choose, well, I have no idea. Well, make that your parameter then. Optimize where these basis functions should sit. That's another way of thinking about it. Third way, which is kind of similar to what I said, is saying that you have a non-parametric model and you're trying to fit the parametric model to that model. Because this model here is not non-parametric in my setting because I've fixed the number of inducing points that I have. Right? So it's a parametric, it has finite dimensionality. Okay? Cool. So this is kind of what I said, that this is my whole thing. This thing here, now we can play around with a lot. Cool. So first thing, what the hell's my prior? Well, the first thing we said that I already hinted to, if I want to fix the scale of something, I can put a Gaussian prior on it. Well, works really well. This is what most people do if they don't know anything. The only thing you're now doing is you're penalizing latent spaces that are massive. Okay? Not super interesting, but you can do it. You can also do another thing that you can try in GPy that's implemented in all the kernels, I think. You can put ARD is equal to true. What happens then is you put a Gaussian prior over the latent space, but you allow the Gaussian prior to basically be different in different dimensions. So what you can do now is you can learn the scale of this thing. So it's called automatic relevance determination, and we're going to use it a bit later on. Another thing you can do is you can put dynamical priors on it. So you can say, I want an x which is sequentially reappearing. So I have a model that says given x0, I can predict x1 and so forth. What you can do, because x was just really nicely separated, you can actually just put a GP that predicts over x. Right? So an autoregressive model to do that. This is a really cool example from a friend of mine, Raquel. This is a paper from 13 years ago. So what she did was she had people walking in a circle like this. And now that's like 50 dimensions or so of my joints moving around. But actually it's only 2 dimensions, right? Because it's a circle. So she learned the GPLVM in 2 dimensions and she found normal people walk like this. Cool, it's a circle. There's some deviation of how the walk is. And then she learned herself. And she looked like this. So that's a bit weird. Turns out that Raquel had a basketball injury when she was young, and she didn't really know that she walked differently. But when you actually learn the 2-dimensional space of it, her stride is very different with one leg compared to the other. So this is like, say, that the left foot and this is the right foot. And it was kind of cool that this just pops up, right? You can't see it in the 45-dimensional space, but here it just popped up very naturally. So that's one thing one can do. So lots of priors that you can formulate. It's just the knowledge that you have of it. So another thing that you can do is you can think about latent space structures. So if we think about what we're often doing, or what we're doing all the time when we're doing models, is that I got some data, and then I say, I want to explain this data by this x through some mapping. And then I add some noise, right? What we're effectively saying is that we're doing this, right? We're saying that f is y minus this, or plus, it's Gaussian, right? So it doesn't matter, but say that it's this. So what we're really doing is we are saying I add noise, or another thing here that's supposed to explain away the variation that doesn't come from here, so that this thing can only explain the important stuff in here. That's the concept of explaining away, right? So now, what would this mean non-parametrically? Well, now you can do lots of interesting things. So let's say that I have this. I have some data, and I think there's some noise. There's some Gaussian stuff that's happening. So first I explain away that, plump. Then I say that this data is generated by a certain set of factors, and I want to explain away these factors. So say, for example, I want to figure out, I have measurements of a human, and now I know each human has an age and a weight and a height or something. Now I really want to explain away the stuff in here that comes from the height. Well, can I now specify a prior distribution over this so that this ends up saying, cool, I'll explain away the height, this explains away the weight. So now, because of this, this will be everything in the data that doesn't come from this, right? This is the classical thing that was called factor analysis. People try to explain what the intelligence was with this, right? So there's an idea of general intelligence, and people formulated these kind of weird models, because if you're good at everything, apparently you're intelligent, was the idea. So this thing here, we can also do with GPs in a very nice way. So one way of doing this is just an example which Neil talked briefly about yesterday, but that is to present the data in an aligned manner. I'm going to explain what this means. So let's say I got this data of images. So there's some strange objects here. Now what I'm going to do is I'm going to specifically pick ducks and cats. And now I'm going to say a data point is a duck and a cat in the same rotation, right? So then I'm going to create a model which, in this case, if I want to explain this data, I know that everything here is ducks, and everything here is cats, but they share the rotation. So if I explain away the duckiness and the cattiness, I end up with rotations. And that's quite nice, right? I can also say that I'm going to put ducks and ducks aligned with each other, but they have different rotations. So now my factorization would be, here I have to explain away rotations, and then if I explain away rotations, I can explain all of that with duck and cat, right? Or another scenario, let's say I want to classify cats from ducks from cats. Now I can say one variation is the class and one is the image. Now first I would then explain away everything in here that's irrelevant for doing the class, which would be the rotation. Here I would explain everything that's relevant for both of them, which is if it's a cat or a duck. And here I would explain everything that's ambiguous to solving this task. In this case, I don't think there is anything that's ambiguous, but you can see how this works. So you can do these models. It turns out it's super easy. So the only thing you do is that you say, well, I'm now going to have cats and ducks, or whatever you have. You pair them like this, and then you say, right, I'm going to have one latent space, and I'm going to have one GP that generates this and one GP that generates this. But then I'm going to have a set of weights, ARD weights, and these weights, remember this Gaussian blob that I have over the latent space? This Gaussian blob can shrink so that, for example, when I generate this, it doesn't use some dimensions here, and when it generates this, it uses some other dimensions here. Now the dimensions that are overlapping with the ARD weights will represent everything that exists in both, and the stuff that's not will exist just here, and so forth. You can also do this model where you say, but I have no idea how I should split up the data. Now what you can actually do is you can put another stochastic process over that. And there's a stochastic process called a Dirichlet process that allows you to do infinitely many partitions of data. And we had a paper at ICML on this, which is used a DP and a GP jointly together. So not going to talk more about that, but it's an interesting paper to read potentially. Okay, did you get that? That's just like, how do I present my data? How do I build a model by just constructing it in different ways and use the parameterizations that I have with GPs to learn factorizations of data? It's kind of cool. Yeah.
Question about your graphical
Yeah.
plate diagram, if you could go back.
This one, yeah.
Would this also work, say, for like feature selection where X is known?
Yeah. Absolutely, absolutely. You can have certain things which are known, certain things which are not. Absolutely, no problem at all. Like, it's easier, right? You can make certain things known. So, for example, what you could do, oh, well, nearly drew here. You can say, like, cool, actually, I can add something that also goes in here but doesn't go in here, and it can separate things up nicely. It's quite cool, and it works surprisingly. This was what Neil said, the thing that wasn't really interesting, but turned out that it worked. So another thing you can do is that when I have this latent space that I want to parameterize, what I can do is I can say, well, actually, I want the latent space to be a function of my data, right? So rather than parameterizing, keeping X as parameters that I do a distribution over, I can implicitly parameterize X through a mapping from my data. This is what's called a back constraint. The reason why I haven't drawn a proper graphical model arrow here is that if I draw that, everything in the whole world breaks. Anyone who thinks that there's something called an autoencoder are fundamentally wrong, in my view. There's no such thing. It's an impossible model to write because it leads to this beautiful distribution. And as soon as you told me what that is, then, yeah, we can talk later. But what this is a back constraint. It's a constraint that I put on a model. But autoencoders doesn't exist. It's weird. So, a last thing on these structural things that I can do is that, let's say this, right? So, if you think about this GP prior that I had, now I've seen 1 point. And now you remember the way we parameterized the kernel was that we said, how much information does knowing this point tell about this? So how much do they co-vary, right? And then we said, like, this would be the variation around that. So this point here varies a lot with knowing this. It provides very little information. But say that I had this, right? Damn it, this is really annoying, right? Say that I had that this point varied a lot. This point is a lot less informed about this region than it is about this. Okay, you can sit and construct a really cool kernel function that implements this and all sorts of stuff. The other thing you can do, so this is a regression setting, the other thing you can do is say, well, cool, let's expand the input space. So let's actually not make this a one-dimensional problem, but a two-dimensional input. And this second dimension that I have, for these points here, I'm just going to shoot them right into the screen so they go further away. Because as long as these points here, are effectively further away from this point than these points, I get this behavior, right? So rather than thinking about, oh, I can construct this really complicated kernel function, you can think about it non-parametrically. Let's just add some latent spaces that does these kind of tricks. So one thing that you can do with this, so this is some work by Eric Bodin in Bristol. So you can do this discretely. So say that I want to model this with the GP. Well, good luck, right? It's no function. Well, let's add a third dimension that takes these points and moves them. So if the data looks like this, now I move it up here, and I just move half the points there and the other points there. Cool, now it's just GPs. Super easy, right? No problem. So then you can actually model this as two GPs. Looks like this. No problem at all. Another thing you can do is if you've got non-stationary data, you've got this really weird thing. Cool. You can represent this using some really complicated kernel. The other way of thinking about it, add this third dimension. This is just the sine function where you're now looking at the projection. I'm going to try and walk as a sine function, by the way. So now this here is me walking along the normal sine function that we normally model. I'm going to add a third dimension. And in the beginning, I'm doing this. Then I want it to go quicker, right? I'm in the middle step. Cool, so I'm now just going to do this. But we're projecting the sine function down here, so it's going to go really fast. And then here it goes slowly, so then I have to walk planar, right? Simple thing. It's just adding a conditional variable, another latent variable that does this to you. Super simple. Really easy, works super well. So now, that was what I was going to say about structures and how you can use latent variable models to do these things. Hopefully, this was useful. Now, Neil was my supervisor, and he had a rant yesterday, and he talked about the golden goose and all sorts of things. So I also learned a lot from Neil. So now I'm going to go with my rant. So now I'm going to have lots of opinions, and it's going to be even more hand-wavy. So let's talk about composite functions, because there's one thing that was blatantly obvious from the variational bound that I did. Well, why don't you put the GP as a prior that generates X? And why don't you take the input of that to have generated from another GP and so forth? Now you got what's called a deep GP, right? So before, we had this, right? And I told you how to integrate out this, and the X term just popped out in the KL divergence. Well, let's just say that that X term comes from a GP, and let's just say that that X term comes from a GP, blah, 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 deep GP. That's how it works. So you can do this. This is kind of cool. Why would you ever want to do this? So now, rant number one, please stop calling things deep, because it adds lots of strange things to it. Why can't we just call things composite functions? Because that's what they are, right? Please give mathematicians some respect. They've given us a profession, so let's just call them composite functions. So why would they ever want to learn composite functions, right? Why would I ever want to do this? So the first motivation that we always see in these papers are, cool, there's different levels of abstraction. So I learn a human being, and a human being is a face and it has eyes. So first I learn the eyes, and then the mouth, and then how these are combined and put together. What did I just describe? Not a composition. I described an additive structure. A composition would be, first I take a nose, then I push an eye through a nose, and then I push that through hair, and then I get something. It doesn't make any sense at all. Like, these abstractions that people draw here, it's nonsense. This is not what the composite function does. It's something completely different. What the trick is how people see this, is if you look at not at one layer in specific, but you look at everything that went from the first layer to that layer. That makes sense. But no single thing in itself makes any sense whatsoever. So, the other thing is, why would you ever use a composite function? Well, the first thing I learned from linear algebra, or algebra in general, is that what is the only characteristic that I care about when it's composite functions? Well, I have the kernel and the image of a function. So the kernel being all the points that maps to the same point, and the image being the number of points it maps out to. The one thing I know about composite functions is that the kernel can only ever grow, because as soon as I have a function that's not monotonic, 2 points are definitely mapping to the same place. So the kernel increases and the image decreases. So as soon as I make a composition of functions, I can map to less values. It's the only thing you do, right? You decrease the diversity in the output of the function. You don't increase it, you decrease it. So let's think about this probabilistically. So there's one nice thing called the change of variable theorem. So if I have a distribution and I want to go from one distribution to another through a mapping, right? We know this through sampling. So if you want to sample from a Gaussian, how do I sample from a Gaussian? How does it work in the computer? Well, it works like this. You compute the conditional distribution or cumulative distribution, bonk. Then you flip this, the inverse in the previous formula. Now you take a uniform distribution, you sample from that, and you map that through here, and you get a Gaussian, right? That's how distributions work. So now, there's nothing saying in this formula, effectively, if I don't care about this being a distribution, the function that I use doesn't have to be monotonic. So let's make a toy example. So let's take a uniform distribution. I got a big chunk of stuff. I map this through this monotonic function. Bonk, that's going to look like this. Now I'm going to say, well, my task in the world is classifying cats from dogs. These are cats, these are dogs, right? Then I'm going to say, cool, let's now do something non-monotonic. So I'm going to add this function to map this through. Cool, we flip this around, bonk, bonk, bonk. Now I do this mapping again. I end up with these. Or actually what I ended up with was actually this. So what I've now done is that I've taken a uniform distribution, which is infinitely many values, and I mapped it to 2. Right? This is great if you want to do classification and things like this. Why is it dangerous? Because if I move from here to delta, 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 tiny bit here, I'm not jumping a tiny bit away from here. I'm jumping between the modes, right? Completely. So my uncertainty in this is completely gone. The concept of actually interpreting this doesn't even exist, right? I can be so damn certain that this is a cat, right? But it can still end up in the wrong place here, and completely wrong thing. Because the only thing that exists here is cats and dogs. So to me, the way to interpret this is to go back to the good old David Mackay. So have you seen this plot? Cool. So this plot is supposed to show why we are righteous and good being Bayesian, okay? But it has a strange thing. So what it says is that if I have all the data in the world, and I organize the data from the simplest data to the most complicated data, and then if I now compute the evidence, so where does my model place probability mass for 3 different models, the model that I should choose is the model that has the highest probability, so this one. Because this one, in this case, this one's too complicated, it explains too much, this too little, this is the perfect one. Great, this makes perfect sense to us, except for that thing I started off in the beginning. How do I sort the data from the least complicated to the most complicated? Well, that's your prior assumption. Your prior says what do you prefer and not, right? Flat Earth or not flat Earth, it's simple for different people. What happens when you do composite functions? You're effectively rearranging this space. So what I'm effectively doing is that I can generate the craziest stuff. What you saw there, I had a uniform distribution collapsed to 2 delta functions. I basically said the whole data space is here. That's it. Now I can put a super simple distribution over this. So what compositions does, everything up to the last layer, if you want to do, is rearranging this space. And if I'm rearranging this space without control, then I've lost everything that I know of what is simple and what is hard. So I can no longer judge my explanation. Okay, so why then ever should you use composite functions? Why ever? So there's 2 scenarios where my generative process is composite. These things exist, a lot of them, because that means my prior knowledge is composite. And everything in learning is about putting your prior knowledge into the system. Or another thing where I potentially want to reparameterize my kernel by moving the inputs using a function, but that can only work if I have knowledge of how I want to reparameterize it. So let's take an example of the first case. So what I have here is a project which a student called Marcus Kaiser did. So he works on wind farms. Wind farms, really cool. So now, the effectiveness of a modern wind farm is about 25 to 60% of what's called the Beats limit. The Beats limit is one really cool physical factor. What it says is that how much air can you take out of a propeller? Like the kinetical energy. You take out 100%, the air is going to stop behind it and propeller stops spinning, right? So the Beats limit is the limit of what you can take out. So these wind farms are not particularly efficient. And one of the reasons for that is we can't model them. But we know shitloads of these things because they're built by Germans, right? They know everything. So they also have loads of parameters, right? So how do I optimize this system? Well, let's think about the generative process of how a wind farm works. So I got some air, some wind coming, it blows, and then it hits these turbines. You take out some energy. This is the only thing I can measure. Then, behind these, turbulence and bad, weird things happen. So now all of these speak to each other. There's a massive correlation between everything here. So how do I model this? Well, one model is to just say, I can measure all this for 100 turbines, and then I'm just going to model this whole thing, and each one of these turbines has lots of parameters. Well, that's stupid, right? Because these are all the same, and I know a lot of them. So what I want to do is specify this generative process. So what I want to do is the first thing, when the wind hits a turbine, it gets affected by the wind at different times, right? So in order to be able to say that these are the same, I first have to align them. So what I'm going to do is that the wind at some time affects turbine 1 and turbine 2, where I now have to transform the time for one of them. Okay? Secondly, now when the wind, if I model that, comes into the turbine, how does it affect the turbine? Well, it affects it as a convolution. You have to convolve the wind signal with the turbine. So now I have, if I've managed to align these, I now would have a convolution in the second process. Then, if I now know how the wind has affected each of the turbines, how is electricity generated? Well, that's the same from all of them. So now that's just the signal that takes the parameters that are currently at that turbine and generates electricity. This is the only thing I can measure. But remember, I know loads of these things. First, time. I know wind doesn't move at 400 million kilometers per hour. I know that it's reasonably smooth. It doesn't change that fast in time. I know everything about the turbine, blah, 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 blah. If I don't write down this composite process, there's no way I can use this information. So what I can do, obviously, I can now say I have the alignment, I have how each turbine generates electricity, and I have this wind front function, which is the same for each turbine. So this thing is shared between them. This thing is for each turbine. This is time. This is electricity measured. Cool. I put GPs over the whole lots of these. Obviously, that's just the natural thing to do. And then I can learn something. And this actually really, really works. So another example of, what happened? Oh, there it is. Another example, which Yeva is going to talk a bit more about, is alignment. So if I've observed these signals, I know that these signals are temporally shifted between each other. So what I want to do is that I first want to take these signals, push them through a warping, get this, and then model them. That was the graphical model of that. Another thing, which I said, if I have this scenario, one scenario that we said is that I can put latent variables on this to move it. Well, another way is saying I can also transform the input space to get this. This was effectively what I did, but I did it non-parametrically. If it's easier to think of that knowledge, cool, please do that. But this can only ever be one layer. I still can't understand or fathom why you would ever want to have a model, if you don't have composite knowledge, that would ever be a composite of more than 2. Composites of 3, I'm gone, right? It doesn't make any sense. I have no idea what's happening. So, 7 minutes. I'm going to finish this. So the third thing, or fourth thing, or seventh thing is, what does it mean to build priors compositely? So what does it happen? Is it easy to think about what the output space would look like, saying that I can specify really nice prior on each of the layers? Not for me, at least. So let's think about just this simple one. Let's say if each one of these are nice, smooth functions, sinusoidals. Well, the difference between a sine of a sine or a sine of a cos is huge on the output. But if I made a sine probable, I probably made a cosine probable, and vice versa. So my probability on the output, I get really, really confusing things happening. The third thing, or fifth, I stop saying numbers. The next thing with this is, actually, there's symmetries here. Like, so if I take an identity and a sign, or a sign and an identity, it generates the same thing, right? Which one of them should I pick, right? So it's really, really hard to learn in these settings. So I wanted to then show that what happens when you specify priors over layers and how this destroys the intuition of the output. This is some slides of a normal DPP, and the first thing, which was cool when it came out, was that people said, great, you can learn step functions. So this is a 4-layer GP learning a step function. To me, this is like, great, this shows that I should never use this model. Because what I've said, I placed a prior on infinitely smooth functions, and you learn the thing that's not differentiable once. And it loves it. It's super high probability for this. So what you just said, you just thrown out your prior and said, cool, this annoying stuff with GPs that you can put in your prior knowledge, we can avoid it. It's like, okay, this just feels completely counterintuitive to me. So what it's done, right, is that you observe data like this. The thing that you have to do is push the points apart, smooth function, push, 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 squeeze, squeeze, squeeze. Now you've got 2 points left in your space, wink, align, beautiful. But between input and output, it looks like that. But these are all the layers. To me, that's just weird. Or it's not weird. So now, another thing to very much think about. We had a very good question on the first day that said, does this plot actually make sense? And it doesn't make sense. We are so institutionalized as GP people that we love doing these plots. This plot here shows the marginal distribution given these points if I were to ask the question, what do I think the point is here? It doesn't show a distribution over functions. That's the samples. The samples here are not going to look like, you can't choose anything in here, right? It's superly correlated. So what happens when we propagate uncertainty through these? Now, to plot that thing is really complicated because now the uncertainty is correlated. Give an example of that. So let's say I take an identity function. I have a little bit of noise around the identity function. Then I have a sign function. Now I push the noisy identity function through the sign function. That means these are the functions that I get. And now I'm going to say I have a little bit of noise around that. So this is now my beautiful plot. So actually, if I take those 2 layers, push uncertainty through, this is what I have. Now, the interesting thing is I could increase the variance of this one, and we could just have a band here very, very quickly, right? So it would look like, cool, this thing hasn't learned anything, nothing at all. Well, if you sample from this, everything is going to look exactly like a sign function. It just doesn't know where it is, right? This we don't capture, and especially when we use likelihood functions, which are just checking, oh, I'm here at the moment, am I likely? I'm here at the moment, am I likely under this distribution? So this is a very tricky thing, and what often happens when you learn deep GPs is that what you can see here is that as soon as I have uncertainty, the uncertainty can never ever disappear. So as soon as you add uncertainty, it generally just explodes. This is why Arno is going to talk about state space models, but state space, any kind of recurrent model is really hard in GPs. Because the more, if you're uncertain, I'm uncertain of where I am, and I'm kind of uncertain where I went now. And because I didn't know where I was, now I'm even more uncertain, and eventually I'm in Leeds, right? So it just doesn't work. It's very, very hard to think about. So the last thing that I wanted to say, and this complaints about everything. So we talked about the variational bounds on deep GPs. So one thing, does the models make sense? I think they're really, really hard to think about. But then, does the inference of our model make sense? So we know the variational bounds are actually underestimating the variance. So what you can do is you can train your model with a variational bound, and then you can sample from it and get the empirical variance. So the wind turbine data that I showed before, this here is what it learned for one turbine. This region here is the variational uncertainty. That's the uncertainty in the model when you sample from it. If I gave you this plot, you would laugh at me, like, really? Like, I'm not putting that on my wind farm. Like, this doesn't know anything. Well, effectively, it doesn't know anything. The variational bound looks awesome. It's beautiful, right? It's really, really nice. it's just super, super, super bad, right? So they're really, really hard to train as well. This is what you get with a deep GP if you put an enormous amount of prior knowledge. If I put my German engineer in there and all this stuff that I know about it, this is what I get, which is good, but you wouldn't believe how constrained this model is. We basically told it what to find, because you have to, because when these compositions start working, your priors just goes out the window. And that's a scary thing. So with that, 20 seconds. I'm going to finish with a wee bit of a summary. So the first thing, what I said, was that unsupervised learning is apparently super hard. We've all been told that this is really hard. It's not. Supervised learning is the easiest type of learning. If you can get paid by doing unsupervised learning, you're a winner. Because what you do, someone tells you, can you solve this data for me? Here's the £10,000. You just hand it back. I've unsupervised learned this. You didn't tell me what to do, so this is the representation of the data. Right? It's fine. Right? There is no such thing as unsupervised learning. It's ridiculous. Right? You just have a different type of supervision. You want something specific. Right? So I think this separating these two makes no sense whatsoever. So what makes it hard is that relevant assumptions of the data is really hard to do. And because in the unsupervised setting, if we want, we're much less constrained normally, which means I need very strong assumptions about the data in order to learn something sensible. So GPs is great for doing this, because GPs provide incredibly strong assumptions. So what that means, it's very easy to put probability mass over a tiny, tiny portion of the hypothesis space. But the coolest thing is, even though you do that, you still have probability everywhere else. It doesn't exclude anything. But that's the benefit of it, and that's why we can learn from small amounts of data. So then, on the composite function thing, importantly, composite functions cannot model more things. As soon as you add layers, compositions, you model less things. But that's exactly what you want to do, right? So it's just important to remember that. When people say the functions become more complicated, well, they become more complicated in a parametric setting, but in a non-parametric setting, they become much less complex, because the output of them is just getting smaller and smaller. So, yeah, basically what I said. So because of this, because this craziness that the prior basically disappears, they have incredibly high requirements on data. So uncertainty propagation is, in these models, is just confusing. I wish I could say this is how you should represent these things. I don't even know how to draw them. They're just confusing. They're really confusing. And when you think about it, it's strange. It is a bit strange to think about it. So I think the first thing that we need to do is to think about our intuition on hierarchies. We can't just sit and think about, cool, I got a GP, I got a GP, I got a GP, I understand this, I understand this, I understand this. That does not mean that you understand the composition of them. Because, as I said, 4 infinitely smooth functions, step function. Whoa, that surprised me at least. So we need to think about whole hierarchies. And then, in the uncertainty setting, we need to start thinking about what does it mean to correlate the uncertainty. Now it's not just the samples that are correlated, but it's the uncertainty itself, which is very interesting. Cool, and with that, I'm going to be 3 minutes late and end. Thank you very much.